Alright, let's take a look at an even more interesting circuit. This is the analog version of a D flip-flop, which is also kind of like a sample and hold circuit. So let's take a look at the code for this. It's called dflipflop.txt. Now, the behavior of this has been described on the board under a different video, and there's a link to it on the code page, on the page where you're seeing this video. But here's the basic setup. So we have two inputs. We have a data input and we have a gate input. Okay, the data input is D. The gate input is coming into the K side of cell 0, 0. And basically, if the K input is large, then we load the data value into our 2-cell flip-flop. If the K value is small, we recirculate the trapped value in our 2-cell flip-flop. So the load line is 0 to close the gate, and it's high to open it. And all of this is just set up as described in that other video. The actual configuration file looks like this. So D flip-flop, we have a D line on channel 0, we have a load line on channel 1, we have a copy of our D input on channel 2 output, and we have the Q, the output of the flip-flop, on channel 3 of our output. So let's compile this, compile D flip-flop, and then let's run it, engine-D flip-flop, and now we've got our simulation running. Okay, here's the setup. Channel 1 is our load line, so let's raise that up all the way. Channel 0 is our data input, and as we change this, channels 2 and 3 reflect the value. Channel 2 is always an echo of our input, so that's always going to match what's coming in. Channel 3 is the Q output of the flip-flop, and right now you can see the output of the flip-flop is matching the input. That's because the load line is high. But if I drop the load line below the 50% value, this output value is now latched. And as I change the input value, you can see on channel 2 the input is still changing, but the circuit is remembering the value that it was seeing when the load line went low. So my input's very low, my stored value is fairly high. If I raise the load line above the 50% mark, my output now matches my input. And again, whatever the input changes to, the output tracks it until the load line goes low, and now this value is stored, and we can see that stored value on channel 3, and it ignores input channel changes because it's a memory, it's a sample and hold. So in signal processing language, when we lift this line, it's sampling the input, and when this input line drops, it's in its hold state, and now the output here on channel 3 will be preserved indefinitely even though the input is changing. So that's a simple sample and hold circuit, or an analog version of a basic data flip-flop. And it's interesting mainly because it shows these different approaches to defining the configuration we want in a cell. This idea of using an if statement to choose among multiple truth table configurations. Again, this doesn't get executed at runtime, right? This creates a static configuration file which is loaded into the system, but corresponds to the behavior that we might describe in C up here, where we're saying if a certain value is bigger than or equal to 32, we want the output value to be this, otherwise we want it to be this, LVAL or RVAL. So that's a more complex example, and hopefully that gives you some idea of what your code can look like, as well as how you compile it, how you start up the simulation, and how you actually run the engine by feeding it a binary file. Alright, so next video we'll take a look at the actual hardware system, and it works exactly the same, except instead of using an interface like this, I don't have something running over here, so this generates errors. Instead of using an interface like this, we can use a physical box, and this physical box allows us to use knobs to set inputs and look at output values on a meter, but we can also hook up physical devices to take signals and take the output, send it to an oscilloscope or whatever we want to do. So that'll be the next video.